Spot the bug. I think it's over there. Hi everybody and welcome to another seminar from us at Don't Use This Code. Today our topic is spotting the bug. But it wouldn't really make sense for me to get all of you together just to write a bunch of buggy code. I can write buggy code all by myself. I do it all day anyway. Our purpose today is to use spotting bugs in programs in order to learn a little bit more about the basics of Python, a little bit more about how some of the things which we might take for granted really fit together, to be able to understand the bug, not just spot it. And of course, our goal here is to cover as much material as we can, so why don't I jump right into it? This session is orientated around 6 separate questions, 6 separate opportunities to spot one or more bugs, which will then lead into a discussion about some fundamentals of Python to give you a stronger understanding of how to use the language that you've chosen to use as part of your work. Why don't we jump right into the very first question? This question is titled, "Why do you keep stringing me along?" In this question, we're going to talk about the difference between the string and the bytes type and what they really mean. We're going to talk about why you encode and decode and why you encode in one direction and decode in the other direction. There are some things we will not talk about in this section. We won't talk about why file paths are strings in Python. They really should be bytes. We won't talk about why certain APIs, like certain SSH APIs, return strings when they really should be returning bytes. We won't talk about why bytes.upper is implemented. It doesn't really make sense. And if you really think about it, why is string.upper implemented? That also doesn't make sense if you don't know what human language the string is written in. We won't talk about any of those. Those are all possible follow-ups. Instead, here's what we're going to do. I'll show you a little bit of code and see if you can spot the bug. I'll just give you a couple of seconds. Can you spot the bug in this code? Did you spot it? Let me run the code and let's see. You cannot concatenate string to bytes. What the heck does that mean? Well, one way that you might go about maybe trying to fix this code is you might try and use an F string and see what happens. And when you do that, yeah, it works. But this is still a bug. It's not a bug in the form of an error that occurs, an exception that is raised. It's a bug in form of, I was intending to print the host name and the user that I'm logged into this machine as at the screen using these command line programs, who am I and host name, and it gave me absolute garbage. It gave me a B and a /n before and after those. And maybe I might try to fix this by doing a .strip to remove that new line, but still, I would expect this to be my name at the machine that I'm running on, and that's not what I see. In fact, what I need to do in order to make this code work is I need to first decode this, whatever it is, and then strip off that white space. This is the working code. And one thing that you might have thought if I had shown this to you in the first place, these extra spaces, are they a bug or not? In fact, they are not a bug. You can actually put as many spaces as you want between method calls in Python as long as they don't last more than one line, in which case you might have to parenthesize this. In fact, in pandas, we do this all the time. We have multi-line dotted expressions that we use in order to keep all sorts of computations we're performing on a data frame all in one place. Now here is a related bug. And you won't be able to spot it because you don't know what the data file contains. But let's say somebody gives you a data file and they tell you this data file contains human languages. I want you to read it in and tell me what language is this data file. Maybe these are languages that our users need to have support for. And you can see this file not found error. Actually, I really want a Unicode decode error here. And so maybe I just need to make sure that my file is available. But if it's not, in this particular case, what we would have gotten or what we should have gotten is a Unicode decode error. And you might wonder what the heck that Unicode decode error really means. And you might have seen that you have to do something like add an encoding parameter here. And when you add that encoding parameter, it works. And you might have wondered what that encoding parameter is all about. But in fact, what we're here to talk about is not the narrow bugs that you might see in your code, why I have to do this decode, why I have to add this encoding parameter. We're here to talk about a fundamental distinction that exists in Python between two things. You have this thing called an str, a string, and you have this thing called a byte string. And they're both called string. They both have string in the name. What's the difference? The difference is actually very clear. An str is human textual data. What is human textual data? Human textual data is, for example, a person's name, their address, a message that you want to print to the screen. All of these are human textual data. Bytes is raw byte level data. What is raw byte level data? Data as it is stored on disk, data that comes out of a command line program, because command line programs don't pass text strings around, they pass byte strings around, data that is passed over the network. Those are all raw byte level data. So for example, you might have seen a string that looks like this. And in this string, you can see all of these special characters that do not appear in the ASCII alphabet. You can see diacritics over the E, over the I, over the N, over the U. And this is completely valid because those diacritics are part of human textual data. They appear in people's names. They appear in place locations. But if you try to do the same thing with this thing that we call a bytes object, which we denote with the B at the beginning, you get a syntax error. You get a syntax error because this B object can only contain byte level data. And you might look at this and say, well, those aren't byte level data, those are characters, A, B, C, D, and E. But if we dig a little bit deeper, we can see that when we created this byte string, A, B, C, D, and E, we were actually creating some piece of data that contained the numbers 61, 62, 63, 64, and 65. And the way that I know that those are the numbers are, this byte string is a way for us to use ASCII values to encode raw byte level data. If you ever iterate over a string, you might see it gives you each character, strictly each Unicode code point individually. If you ever iterate over a byte string, you might see that it gives you the numeric values of what's contained within. A byte string is raw byte level data, and you can write a byte string literal in your code by giving it the actual numbers that it contains, 61 in hex, 62 in hex, 63 in hex, or their ASCII equivalents. In the ASCII alphabet, A is equivalent to 61, E is equivalent to 65. What that means is when you have human textual data, people's names, addresses, messages you want to print to the screen, you need to figure out how to store that on disk somehow. You need to figure out how to send that over the network. And on disk, it deals with bytes. It doesn't deal with human language. It doesn't deal with how you interpret those bytes. It deals with the underlying bytes. When you send it over the network, you have to figure out how to send those bytes. And you might also compress it. Things like compression and encryption. They don't work on human textual data. They don't work on human names. They work on the underlying bits and bytes that are used to encode that data. This is why when you have a string in Python, you dot encode it. And there are multiple choices for encoding. I run on Linux. And on Linux, it's very often for the default encoding to be UTF-8. This is a Unicode encoding that tries to fit as much as it can into 8 bytes. It is an encoding into 8 bits. And it is an encoding which is actually a strict superset of ASCII. So everything that is valid ASCII is valid UTF-8. If you happen to be on Windows or an international version of Windows, it's very likely that your default encoding is ISO 8859-1 or Latin 1. Those tend to be the very common default encodings that you see on Windows, especially both domestic versions of Windows and international versions of Windows. And what you can see from this output is the way that UTF-8 encodes those special characters like the E with the accent on top of it or the N with the accent on top of it, it's different between UTF-8 and ISO 8859-1. Latin 1 and ISO 8859-1 line up quite a bit, and in fact, I'll tell you a secret. All 3 of these are strict supersets of ASCII, so the raw ASCII characters, the regular unadorned A to Z lowercase, A to Z uppercase, they're going to be the same. It's only those special characters that appear in languages like French, Spanish, German, and languages outside of the Latin family, languages like Chinese and Hindi and so forth and so on. This is why you have to supply that encoding parameter, because that original bug that we saw when we tried to load that file, unfortunately the file was not found, but you can imagine what happened, what should have happened. What's happening there is probably I had a colleague who had a file that they had some data in. They were probably using Windows. They probably didn't specify the encoding, so it used the default encoding. It probably wrote the string out kind of like this. When I read in the file, I was reading it in on Linux or Mac, and my default encoding was different because neither of us specified the encoding. It got written in one format and then reinterpreted in another format, and we run into an error. And that's what that Unicode decode error often is a result of. And so for every one of these bugs, we should always ask ourselves, what do we do about this? How do we actually incorporate this knowledge in our life? Well, remember this. Strings are human textual data. If it's something that makes sense to a human being that's meaningful in the human world, it's a string. If it's raw byte level binary data, then it's a bytes. The way you go from one to the other is you encode a string to figure out what its encoding is in bytes. And you can specify what that coding is, UTF-8, UTF-16. UTF-16 is deeply baked into the internals of parts of Windows. ISO 8859-1, Latin 1, Big 5, GB 2332. These are all common encodings that you might encounter based off of the, I think it's 2312 actually for GB. But these are all common encodings that you might run into if you're working with different operating systems in different localities. If you have raw byte level data and you want to turn it into human textual data, you have to interpret it. That's why you decode it. Decode means interpret. You have to decode the data as it exists on disk, the data as it's sent to you over the network, the data as it appears in that format. And when you decode it, you have to know what the encoding is. If you don't specify these, it will use your system default encoding, which if everybody's on Linux and everybody sets it to UTF-8, everything's easy. But if you're working with international parties, if you're working across nations, if you're working with different localities, if you're working with different operating systems, it could very well be the case that they're not. And so when you are reading and writing data, be careful to specify the encoding. Or don't write raw data files, write JSON data files or XML data files, because here's how JSON gets around the problem. JSON presumes everything's UTF-8. You can't use any of these other encodings except UTF-8 and JSON. It's part of the JSON standards. And as a consequence, if you were to write a JSON file and then have somebody read it, and you were to use things like the standard library JSON.dump module, well, no big deal, because it will presume everybody's going to use UTF-8 and you wouldn't run into this problem. And so always, when you're working with something that you might call a string in Python, distinguish between, is this human textual data or is this raw byte level data? Our next question is titled, does it float or sync? In this question, we are going to talk about the difference between the float type in Python and the int type in Python and what they really mean. We'll talk about what the minimum and maximum value of a Python float or int are, and we'll talk about key considerations for working with Python floats, namely IEEE 754 binary double precision floating point types, what this notion of inexactness and imprecision are, and how they affect us in our lives. As a follow-up, two things that we won't discuss are the other two built-in numeric types in Python, complex and bool, and in specific, why is bool in Python intentionally, purposefully considered a numeric type? How would that even be useful? It's a great follow-up, but we won't have time to cover it because we're going to spot the bug. In this bug, I have some JSON data. I'm going to load it in, and I'm going to try and range from some starting point to some stopping point and some stepping point. And I'll give you a moment to spot the bug. I wonder if you spotted it. This is an actual bug that I've seen in real code that affected me in one of the projects I worked on. We were doing a power sweep as part of a mesh optical network planification project, and somebody wrote this code and it didn't do what they expected. This is not a syntax error. This is not an error that will appear on the screen. Or rather, in this particular case, you'll see an error on the screen. You'll see a type error because range requires integers. But you might say, oh, the bug is that I'm using range, and if I'm going to use range, I need to give it integers. Okay, fine. Or the bug is that I'm not using a range from NumPy, but can you spot the bug here? There's still a bug here. Even if I swap this out with a range, there is still a bug. Can you spot the bug? There's still a bug here. Can you spot it? Something weird happens. This gives me 1.0 and 1.1. When I did this with the range, and I did it from range from 10 to 11, stepping by 1, it just gave me 10. And a big question is, this is not a syntax error. This is a logical bug. This is a mistake. Whenever you see some sort of interval, something that has a lower bound and an upper bound, the first question you gotta ask is, what kind of interval is it? Is it open? Meaning, you don't include the lower bound and you don't include the upper bound. If I say from 3 to 7, including 3, including 7, or just the numbers in between? If it's just the numbers in between, that's an open interval. If I say this is a closed interval, then the lower bound and the upper bound are included from 3 to 7. That's 3, 4, 5, 6, and 7. Or I could be talking about a half-open interval. And a half-open interval is an interval that includes one end but doesn't include the other end. So it includes the lower bound but excludes the upper bound, or vice versa, excludes the lower bound but includes the upper bound. Generally, with very few exceptions, and I can only think of 3 common ones off the top of my head, Python generally sticks with half-open intervals. It generally excludes the upper bound. So if you do, for x in range 3, this is from 0 up to, but not including 3. If you do from x, range 1 to 3, again, it'll be 1, 2, but not the 3. If you use rand range from the random module in Python, and you say, give me all the values in rand range 3, it'll give you a 0, it'll give you a 1, it may give you a 2, it will never give you a 3. It excludes the upper bound. If you use slicing notation in Python and you say, give me all the letters in this string from position 1, bear in mind, we're counting from 0 up to 3, it's going to say, well, this is position 0, this is position 1, position 2, but I will not give you the character at position 3. One follow-up for you is, can you think of the 3 things that I'm thinking of in the entire Python and PyData ecosystem? Or I'll even be more specific. I can think of one thing in Python, and one thing in Pandas, and one thing in NumPy, which don't obey this upper bound, lower bound distinction. I guess the one in Python is a little bit hokey, but I can definitely think of one thing in Pandas, and definitely one thing in NumPy, which don't exclude the upper bound. In general, whenever we're working with these intervals, we're working with these half-open intervals. But if I look at the output of A range from my buggy code, something weird arises. If I do an A range from 1 to 3, it's 1 and 2, not including 3. If I do an A range from 1 to 4, it's 1, 2, and 3, not including 4. If I do an A range from 1 to 1.1, stepping by 0.1, the 1.1 is included. And if I go up to 1.2, and it's not included anymore. And if I go up to 1.3, the 1.3 is included. This is very strange. What's going on? Well, this tells us a little bit about the built-in numeric types in Python and also a little bit about numeric types in general. In Python, you have an int type. It represents a whole number, what you might call an integer or what you might write in this Blackboard Z if you were a mathematician. This represents some sort of discrete quantity, like a count. They say the average American has 2.3 cars. What is 0.3 of a car? Is that just the steering wheel and the front 2 wheels and maybe the passenger side airbag? That doesn't make any sense. When you're counting things, it's either 1, 2, 3. There's no such thing as 3.5 of those. Float, on the other hand, represents a real number. What a mathematician would write with a Blackboard R, it is a real number, a continuous number. It represents a continuous quantity, like a physical measurement. Typically, we can think of physical measurements like your height or a span of time as being continuous, even though you could also say that, at a very strict microscopic level, maybe everything in this universe is discrete, but still, when we talk about measurements, we're typically saying, 1.35729 inches, that makes a lot of sense. Well, integers and floats in Python are handled very differently. For example, there is no such thing as a maximum or minimum integer in Python. Here, the number 2 is clearly an int. Python told me so. I can raise 2 to the 20,000th power, and it gives me so many digits. I could just keep doing this as long as my computer still has RAM. There is no such thing as a maximum int. There is no such thing as a minimum int. There is no such thing as underflow or overflow in Python. Dead stop, as long as you're working with ints. But if I work with floating point values, this 2.0 is clearly a float, and I raise that to 20,000th power, I suddenly see overflow error. And I can see an underflow error. There are maximum and minimum floating point values. In fact, Python hews very closely to the IEEE 754 double precision binary floating point standard, the same kind of floating point values you use in Java, in C++, in C, in raw NumPy data. These are the floating point types that you are very familiar with. And they do have a min and max. I say it's double precision because this is what you'd call a double in C or C++. It is a 64-bit floating point type, and it has this maximum number. Boy, that's big, 1.7 times 10 to the 308. And the minimum is 2.2 times 10 to the negative 308. That is a huge range of values. You might think that sys.max size is the maximum integer size, because in Python 2 they used to call this sys.maxint. It is not. There has never been a maximum integer size in Python. In Python 2 there was an int long dichotomy, so the ints would automatically become longs. But in Python 3 they eliminated that dichotomy, or at least they eliminated it from your perspective. And so this just represents the maximum size of a Python container, not the maximum size of an integer value. But a question arises. What floats in floating point? Sometimes when you're working with floating point and the result you get doesn't make sense, I think your head kind of floats and you're like, oh my goodness, what's going on here? This makes no sense, and I'll tell you why. Think about how you would represent a real number, a continuous number, in a finite number of pieces of memory. So let's say you have 9 memory positions and you want to store the number 1234.5678. Well, you'd store in memory position 1, the number 1, then digit 2, then digit 3, then digit 4, then you store the period, then you'd store 5, 6, 7, and 8. And you'd say to yourself, you know what, I'll just make my convention. The first 4 memory locations are the things to the left of the decimal sign. The last 4 are the things to the right of the decimal sign, so I won't store the period. I need 8 pieces of memory. And when you do that, you discover that your maximum and minimum floating point value are 9,999, and your minimum magnitude, not including signed and unsigned values, just the minimum and maximum positive value, is 1/10,000th. If you were to say, oh, you know what, I'm going to say that the first 2 digits by convention are the things to the left of the decimal point, and the last 6 are the things to the right of the decimal point, then it affects your min and your max. You have a max of 100 and you have a min of 0.000001. Well, think about this. The designers of IEEE 754 wanted to serve a variety of use cases. They wanted to serve the macroscopic use cases and the microscopic use cases. They wanted their code to make sense if you were doing things at the astronomical scale because you're an astronomer, or if you're doing things at the microscopic scale if you're a particle theorist. And as a consequence, any place that they choose to put that floating point digit is either going to take away from the maximum value or take away from the minimum value, unless they allow the floating point, unless they allow the decimal point to move around, unless they allow the decimal point to float. That's what's floating in floating point. The decimal point can be anywhere. And as part of the encoding, you store where that decimal point, in so many words, you store where that decimal point is. In fact, IEEE 754 is a little bit more complicated than that. There's things like normalization, and it's actually storing, the exponent separate from the fraction. There's quite a bit of theory there, but in general, the idea is that the floating point can, or the decimal point can move. And as a consequence, you can store huge macroscopic values or tiny microscopic values. But this creates 2 problems. Some of these problems are not specific to IEEE. In fact, some of these problems are fundamental to the idea of having finite memory. But here are the problems. In decimal, you cannot exactly represent 1/3. You've done this before when you were a kid and you got your first calculator. You computed 1/3 and it gave you 1.3333333, and then you multiplied it times 3 and it gave you 0.99999, and you said, wait a second, 1/3 times 3 is 1. What went wrong? Well, we know that 1/3 in decimal is not 0.333333, it's 0.3 infinitely repeating. But infinitely repeating presumes you have infinite memory, and you don't. You have finite memory. In the floating point standard, you only have 64 bits. So you gotta cut it off at some point, and when you cut it off at some point, you are saying, I cannot exactly represent 1/3. But because IEEE 754 is a binary floating point standard, not a decimal one, the things that you cannot exactly represent are not the things you can exactly represent in decimal. Like 1/3, 1/6, 1/7, 1/9 cannot be exactly represented in decimal, and I'll correct my error here. 1/10 can be represented exactly in decimal, but the rest cannot. In binary, you cannot exactly represent 1/3, 1/5, 1/6, 1/7, 1/9, 1/10. In fact, the way you can think about this is, if the base that you're working with does not share prime factors with the number that you're trying to represent, or at least the denominator of the number you're trying to represent, you cannot exactly represent it. And so 0.1 cannot be exactly represented in a binary fixed number of digits floating point standard. It appears to be exactly represented, but that's a trick of the interpreter just to try and give you an output that looks kind of like the input that you have, and a lot of research is put into that. But if you start adding up 0.1, you'll start to see it's not that the error is accumulating so much as none of these were exactly represented, and at some point Python cannot figure out how to give you back exactly what you thought you were giving it, and it's beginning to show you that error. And so here you can see 0.3 in binary, the closest they could get, they had to cut it at some point, was with that little 4 at the end. And you'll see this for all of these inexact fractions. They cannot be exactly represented in binary, and that's what's going on in our bug. What was happening in our bug was because 1.1 could not be exactly represented, and because arange is adding and adding and adding until it exceeds a value, what happened was that 1.1 was just slightly above, as it was represented, the repeated addition of the 0.1. And so it was contained within, or the 1.1 that we saw on the screen was actually contained within the interval. It was still a half-open interval. It's just that this inexactness here resulted in us going a little bit too far past what we consider to be the upper bound. Now, we didn't see this in our program, but there's another bug that you will commonly see when you work with floating point. And sometimes it can leave you scratching your head. You said that the decimal point can float around, which means if you're representing a humongous macroscopic value, notice you do not have a lot of precision for what comes after the decimal point. If you have a large microscopic value, well, you don't really need anything to the left of the decimal point. In IEEE 754, it's not like this. They don't actually say, oh, here's some digits and here's where the decimal point is. It's stored as and there's some fancy terminology, mantissa and all that, but it's stored as a fraction and exponent part. And it allows you to store values that are very, very, very large, that are so large that instead of excluding possibilities to the right of the decimal point, they exclude possibilities that are even in the tens, the hundreds, that are to the left of the decimal point. In IEEE, you can even do something like this. In IEEE 754, you can even do something like this here, where you have a humongous number and you just don't have any ability, any precision to store these particular values here. And so this is the breaking point for it. 2 to the 53rd plus 1 for a 64-bit floating point standard where 53 bits are used for the fractional part. 2 to the 53rd plus 1 is the first integer value that cannot be represented precisely by IEEE 754, and you get some weird results. If I add 1 to this, nothing happens. If I add 1 again to this, something happens. How is it that this number plus 1 is equal to this number plus 1 plus 1, and that's not equal to this number plus 2? That makes no sense mathematically, but it's because you didn't have enough precision. You didn't have the ability to store that last decimal point. You had too much money in your bank account. They said, you know what, don't bother to deposit that check with 1 cent. It's not going to make a difference. We'll just throw it in the trash. You're not even going to notice it. That's what's happening here. And you get some bizarre results, like a number can be equal to itself plus 1. Mathematically impossible? It's possible if you don't have precision to store those very small positions. You no longer have associativity or commutativity. X plus y grouped plus z is not equal to x plus y plus z grouped. X plus y plus z is not equal to z plus y plus, and I should put an x here, plus x. You lose these guarantees that you have in integer mathematics, in standard mathematics. And so the question is, what do we do about this? Be careful when comparing floating point values. Don't exactly compare them because you may not have an exact representation number or you may have lost precision. Use things like math.isClose or numpy.close. 1.1 plus 2.2 is not strictly equal to 3.3, but it's close. And you can tune what you mean by close. If you really need to have, a little bit better precision, you can use decimal.decimal from the standard library, which represents numbers as decimal values. And you can see here, 0.1 plus 0.2 is imprecise, or it's rather inexact as a floating point, but it's exact as a decimal. But remember, you have finite memory. Even the decimal module has finite memory. In decimal, you cannot store 1/3 exactly. It doesn't matter how many digits of precision you give this thing, it's still going to be some sort of rounded approximation. And so, you can't get away from that problem. You could use fractions.fractions from the standard library, and in fractions.fraction, a 1/3 fraction times 3 is equal to 1, but that doesn't always work. Not everything takes fractions. And if you really wanted to, you could use SymPy. The reason why you might use SymPy over fractions.fraction is there are non-rational numbers you work with, pi and e. And how do you represent those as fractions? You can't. Well, SymPy can represent these symbolically, but the downside of SymPy is it's going to be way slower than IEEE 754 double precision floating point, which is incredibly fast. That's, you hear people say this new supercomputer can do 10 billion floating point operations or 10 trillion floating point operations per second. Floating point operations per second is a metric that's used to measure the speed of computers to sell you new processors. It is a very fast thing to do. SymPy is all software supported. It's going to be slower. And SymPy is going to be limited by what it can actually resolve. It can only do simplification as good as the symbolic algebra tools that you may have used before on your hand calculators. In general, prefer to use integers over floating point values for discrete values. If you're doing counts, use integers. You avoid this problem entirely. And don't sweat it for simple problems. The first time you lose that precision is 2 to the 53rd plus 1. That's probably more money than you have in your retirement account. Maybe not if you've done really well in cryptocurrency, but it's the case where don't sweat it for simple problems. This does come up and it's something to be aware of, but it's not something that's going to happen in just a simple script that's summing up your grocery list. Let us move on to our next question. Our next question is titled, Are you on the list? And in this question, we'll talk about the difference between the list type and the dictionary type and what they mean. We'll talk about the limitations of a list, but we won't have a chance to talk about the dictionary subclasses, limitations of a dictionary, but we won't have an opportunity to talk about the dictionary subclasses in the collections module, which are incredibly useful and come up all the time in my work, collections.defaultdict, collections.counter, collections.chainmap. We won't have an opportunity to talk about the difference between a dictionary, a collections.counter, and a pandas series, another very interesting distinction, and we won't have an opportunity to talk about what it means to write dictionaries in different ways, what the different modelings mean. What's the difference between what number 1, number 2, and number 3 are capable of, and what they mean about the underlying reality that you're trying to model. Instead, let's take a look at a very simple problem. We have a bunch of animals. We're trying to count the animals. You should have 3 dogs, 2 cats, 1 cow, 1 chicken, and 1 fish. We're doing a little counting. And here is our sample code. We're going to have a list of lists that store our counts, where the first element is the animal, and the second element of that list is the count. Can you spot the bug? Did you spot the bug? The code works, and it runs, and it is completely fine as it is. There is no syntax error. There is no logical bug, but there is a major mistake here. In this code, we're using a list of lists to store the counts. And so every time we have a new animal that we're looking at, we loop over that list, we try and find the corresponding entry for that list, and then we update that entry in that list. This is buggy because as the number of animals that we're looking at grows, the performance of this code will fall off the cliff. This is going to be terrible performance. This is a bug from the perspective of it will immediately bite you in the butt as this data set gets larger. Because what we should have done instead is we should have stored this as a dictionary. And you can see the code here is a little bit cleaner, a little bit shorter, but it is also significantly, substantially faster. Let me show you. And we could have used a default dictionary or a counter as well, but we won't go into that in too much depth. What I want to show you is, in Python, this tells us that there are 2 core built-in types that come up all the time. The list, which represents a collection of linearly ordered data, and the dictionary, that represents a mapping or association of 2 pieces of data of keys and values, which may be ordered if you're using Python 3.6 or later, or may be human ordered. Here's why you're going to see this pop up as a real bug in your code. Here I have a little exercise where I'm going to time something. And what I'm going to time is I'm going to time what happens when I have lists of increasing size. 1 element, 10 elements, 100 elements, 1,000 elements, and so forth and so on. How long does it take for me to look for an element in this list? Now, to make this a fair game, I'm going to look for an element that I'm guaranteed will not appear in this list. This is a list of random numbers from 0 to 1,000. I'm going to look for the number -1. And we'll see how this failed lookup performs. Notice every time the size of my data increases by a factor of 10, the amount of time it takes to find an element in this thing increases by a factor of 10. That is terrible performance. That means if I double my workload, I double my time. We really want to avoid that because I'm not gaining anything. There's no margin here. I'm not making my life easier I'm not using the computer to leverage things which allow me to capitalize on some margin and make a profit. Whereas, if I do the same example with a Python dictionary, what we will see is, irrespective of the size of the dictionary, the lookup time is identical. It's constant. If I have 1,000,000 elements or 100 elements, it broadly takes the same amount of time to see if an element is there. Dictionaries are tools for fast retrieval, for fast lookup. And by fast, you can see, once we get to the very large structure, we are not 1 order of magnitude or 2 orders of magnitude. We are 7 orders of magnitude faster than the approach taking a list. This is a bug, because if somebody came to you and said, oh, I made your code 1% faster, you'd say, oh, okay, who cares? If they said, I made your code 10% faster, you'd say, I'll buy you a Coke. If they said, I made your code 1,000,000 times faster, you're going to say, okay, maybe that's worth dinner. Maybe that's worth getting you lunch. The dictionary type and the failure to use a dictionary type where appropriate, I think constitutes a bug in real code. And I think it constitutes something that you want to fix. The dictionary type is a great type. It is heavily optimized. It is commonly used throughout the standard library, throughout the core interpreter itself, but there are some considerations for this dictionary type. In the dictionary type, the keys must be unique. The keys must be hashable. And if you're using a version of Python prior to 3.6, understand that the dictionary type is machine ordered. It doesn't have an ordering that you as a human being can use as part of your program. After Python 3.6, this gains a human ordering. The ordering is something you can use as part of your program, specifically insertion ordering. Now, when we talk about hashability, what we mean is the keys of that dictionary, this is a lookup. So you look up a key to get a value. The keys of that dictionary can be anything that is an int, a float, a complex number, a bool, a string or a bytes type, a tuple, or a frozen set. And if you look at this, you might say, well, as a shorthand, these are all the immutable built-in types. They're not. There's actually an immutable built-in type that cannot be used as the keys of a dictionary. And in a moment, we may even talk about mutability versus immutability and how that relates to hashability. But for the time being, let us understand the dictionary type has some pros and cons. The pro is incredibly fast for lookup. The con is there's some limitations over what we can actually store in that dictionary, what we can use as the keys. What do we do about this in our code? Whenever we have 2 pieces of data and there is a connection or relationship between them, 2 data sets, and we know this data set relates to this data set in a specific fashion. As a one-way lookup, one element of this data set can map to multiple elements of this data set, and the elements in the left-hand side, the elements that you look up from, are unique, and those elements can be modeled as a hashable type, one of the types that I have above, or something that you can define yourself, that you can define as being hashable, then you should probably use a dictionary, because the performance benefit will be way better than what would happen if you use that list. You won't fall off the cliff. And here's the thing about performance. Between you and me, if I had the need for speed, I'd probably write all my code in assembly. I care about like a 20% speed up, sort of. I definitely care about a 100 times speed up. That takes something that would take, be an overnight batch job and make it into you can actually do it at, in between getting new coffee or new tea from the vending machine. Here's the thing. One of the problems with performance is an over-focus on like the 5%, 3% speed up. They do add up. It does make a difference, but it's not always the most important thing that we do with. However, one of the downsides of dismissing performance as an important characteristic is things can work really well on your testing data sets. Things can work really well in your sample environment, in your QA environment, and then fall apart in your production environment. In the case of the list versus the dictionary, you could kind of imagine where if you did this with the list, it's fast enough for the really small structures that it might just pass through your testing, and then when it hits production, it grinds to a stop, and it is too slow. Now, for the list versus the dictionary, that's not the biggest deal. One of the things to be aware of, and you can see we're beginning to hint at this a little bit, is people talk about this using the terminology asymptotic complexity. They talk about this as being a linear or a quadratic performance. Linear performance is not that great. It can kind of bite you in the butt. Quadratic performance is something that definitely bites you in the butt. It works okay in testing, that blows up production. But this is how I want to contextualize this discussion of performance. It's not always the main thing that you care about, but definitely here, if we're getting 1,000,000 times speed up on very large data sets that we might see in the real world, that's worth it.